So we'll come back to using that TF-IDF score in lots of ways later. But the next thing we talk about then are some algorithms we're coming up with a maybe richer encoding or score for words that doesn't have these drawbacks of missing the context and everything, right? So a very popular one, and I guess it's a while ago now that it was a big deal. 2013. So yeah, it's not that long, but it's getting close to 10 years now, where two people were working on different ways to come up with encodings, or like we're saying, representations of words and documents. So these TF-IDF type things were all kind of hand-tuned. That here's a reasonable one, and people used that, and it was quite effective. And search engines and lots of useful things were built out of them. But in 2013, people had been working on more complex kind of approaches, and this one came up and kind of changed everything. So their idea is that they want to come up with a vector that represents the word, but that encodes its context as well as its kind of frequency and all of these things together, but isn't just a calculation that we do based on counting. It's something that we can build up iteratively, and then come up with this encoding. So we already know about representing the word, the term in the vocabulary by its index. We've got a semi-supervised approach here. It was the first time we were talking about semi-supervised, because we have an answer, but it's not like someone's given us a label. So we're trying to learn the correct structure using the data we have. And so in text, we can do this by using the context, the neighborhood around a word of the other words, basically saying, you know, what follows this word in the text, just like your predictive text on your phone, right? Autocomplete when you're texting on your phone. How do it guesses what the next word will be, right? And so that's this kind of using this context. We have a model that will predict what the next words are going to be. So you could train it based on that text. It looks at all the things you usually type and use the frequency of how words follow each other to come up with its model. And so it's using, like saying, these relative positions of the words and building this encoding. So how does it do this? So there's two main approaches. I have changed the order of all these slides. My notes are useless. Okay, we're showing them both there, right? Okay, that's the order. This is SIBO. So we have two basic architectures here, and it's not really a neural network, but it has all the components of a neural network, and it kind of does a very simple version of one to get just what you'd need for coming up with encoding for text. So we have our bag of words, so we've already talked about, right? Which is just the frequencies of the words in the document, so it just counts for all of them. So continuous bag of words is you're saying, given some words in the text, can I predict one that's going to be in the middle of them, right? Right. So we can remove a word out, right, and ask it what is this, right? And so you'll have counts and models about all the other words, and now you want to predict one of the words in the middle of it. That's the SIBO type approach. And then skipgram approach, you've got some word, and you're trying to predict the words that come after or before it, right? So what was the sentence that came before it, or what was the words that came after this? but you're using the same kind of idea for both. So one view of the structure is here, and I have another window that has some nice descriptions that we can look at later. Yeah, okay. Oh, these are all examples. So the idea, though, is here. So the input layer we've got are the words in the document, but in order this time, right? So actually, all the words in the article you're reading, and the output layer would be the targets that you're trying to predict in that case, right? So if we're trying to predict the word in between, then we are saying that the output label we want is for every, like when we're looking at some set of input words here, then the corresponding word that's the output is the one that we were guessing in the middle. So it could be, you've got 3 words, a missing word, and another 3 words. Then for missing word I, the answer I is the one that was left out of the sentence, right? So when we say that it's semi-supervised, another thing that people say more these days is actually self-supervised. It's kind of the same idea. There's information that we have that we can use, but we're really using our own data sets. I give you one data set of words, and you use that very data sets to as your training data, right? And so you slide a window along the document, and you're looking forward and backward some certain number of words, and you come up with the label yourself, right? Because you're basically knocking out this word in the text and then using the 3 words before it and after it to help you try to predict what would happen. But the labels are all in there, and so every word becomes a label at some point, right? So that's why it says semi-supervised or self-supervised. And sorry, I had like another better description of this somewhere. I'm trying to find it. Oh, maybe that's why. Nope, that's not it either. I don't know where it is. Right, so there's negative sampling as well. So I'm going to show you a better example once I can find it. Let me just go through and see. Right, we have the training process. Yeah, see, I added these, but they're not in my notes that I can view separately. Okay, so we'll go back to skipgram in a second. So how does this work? So we've got a bunch of different parameters for this algorithm that we can use. So we need to know how many words we're dealing with, how big an embedding we want. So this idea of, this embedding here, so this hidden layer, or we'll call it embedding. So this will be the vector, right? So when you input a a word, you want to get a vector out that represents what this word is. And that's where you're going to be getting it from. These pictures are really not very good. We need to know the window size, so how much context before and after each word are we looking at. And then we're going to have this also idea of negative samples, which wasn't in the original algorithms, but people found it was actually very useful. What was in the original word2vec algorithm, but that was one of their innovations, that they added this idea that you can actually learn from pretending to do it wrong, actually. So negative sampling is a very neat idea for semi-supervised or self-supervised data. So yeah, I guess I can have maybe this open in a separate window. This is a very nice website. It had like a description of this. You read the paper and you see it, because this paper is, I mean, it's old, but it doesn't have a lot of figures in it. In this blog here that I've got linked, he's got some nice figures just explaining the exact same thing, but for these matrices. So hopefully people can see that. Okay. So we've got two matrices, an embedding matrix and a context matrix. And like we said, you've got the entire vocabulary. Thank you. Someone's posted the blog post there. Right, your matrix go across, there's a row for every word, and then you're coming up with an embedding. So every word is going to have its own vector that we're going to learn, rather than just using this frequency count. We're going to have one for every word and learn it. So originally, initially these matrices are random, but the idea is that we're going to build a model like we had a picture there of, to take some input and produce an output word. And so in the skipgram model, what we want to do is predict the next word, right? So I have a picture there saying, right, here's the SIBO one where we've got a bunch of context words and we're somehow learning a way to combine them and giving us a prediction of the word in the middle. In skipgram, you're given a word as your starting point, and then you want to predict a bunch of words before or after it, right? So let's just say we're saying we're taking an input word and we want to predict what the next word is, just like your predictive text on your phone, right? So say that's the challenge. For every input word you've got, you could say, well, what's the next word in the text, right? And so we know what the real next word in the text is. So we've got the true output word that comes next. And then we could say, well, what are other words that could come next because they're in the document, but they don't come next, right? So these are our false, our negative samples, right? So we're going to come up with a bunch of words that that are wrong, basically, and say how likely is our model to predict those, right? Because what it's going to give you as an output is to give you a new vector with a magnitude, right? So we're going to do that dot product. So you've got, term I, and then we've got two other terms, K and J, right? And we're going to do just a dot product with each one, not together, but I'll be less confusing. We'll actually compute the dot product of the vector for that, right? So we've got to actually, I don't have any a representation of that. So once we have the actual vector for that word, we can compute the dot product between the two of them, and we get the magnitude and direction of this new vector of a new word. And we use that to basically come up with a probability, right? So we use a sigmoid function on the output number. So he's got the calculations shown here too for some example, right? So the input word was not, and then the output word was these other words that could show up in in the text, not thou, was the correct thing. And so you take the dot product and you get some score, right? You get an actual magnitude. How likely is that? How big is that magnitude of the vector? But what we do is we pass that through a sigmoid function, right? So we had the sigmoid function from logistic regression before already, right? And remember, it's one that turns any number between 0 and 1, between 0 and infinity. I wrote it backwards. Into something between 0 and 1, right? Ignore me today, sorry. It's too early. It's going to give us a probability, right? And so the fact that this magnitude of this vector, it can be in any direction, we're going to turn to a probability between 0 and 1 and treat that as like our confidence that the word is correct. But it's going to be wrong because initially we initialize these matrices randomly, so they're basically gibberish, the way that they're producing their encodings. But they'll slowly get better. And so what you do is you give it a true example, say, okay, that was good, and these ones are wrong, so they're wrong, even though it had a higher score, you know, for one of these wrong ones, not taco is not the next word. But now we can treat that as a negative case, right? So once you've got these probabilities, what we're treating like probabilities, you now compute the error, right? So we take the difference between, I think I have that on my next slide, yeah. We're going to compute the error, so how well did each one do or not, just by, you know, subtracting the true value. So it was supposed to be, right, so the way we're treating the target as 1 or 0. So if it's correct, it's probability 1. If it's wrong, it's 0. And your score is being treated as a probability. So if it matches, then your error will be 0, right? If your model said 100%, it's definitely this word, then you'd have 0 error, right? And basically now you've got positive and negative scores that you can use to update a model, right? And so we do, they just do logistic regression the same way you could do it with your map solution that we talked about, or the other methods that people use to kind of iteratively solve that. And basically what happens is that parts of basically the weights that determine how this word, this index leads to this index, it would be increased because it was correct, and these ones would be decreased because it was incorrect, right? So the mapping that tells you that these words should follow each other would be reduced, right? And so your model will get slowly better. And the encoding will become more correct over time. So you go through all the words in your document, in your menu documents, and update this way, essentially just using logistic regression and lots of little versions of it. And in the end, what do you get? He had a nice representation of word encodings, but he started with that, so it's kind of confusing. You'll get a bunch of scores for every word. So here's the classic example in the original paper, that you've got a bunch of words that showed up in some documents, and now you've got some score that tells you, well, nothing, it's just a bunch of numbers. So it's the encoding for that word, right? Say we decided we wanted the encoding to be, you know, 50 numbers, then you've got 50 numbers here. And whether they're similar or not would be whether or not they're all kind of have the same color and in some kind of pattern, right? The same two words that were very similar would have a pattern that's quite common. So if you look at king and queen, they have a lot of things in common, but not everything, right? And if you look at girl and boy, there's a bunch of stuff that's similar, because I guess it's irrelevant to gender, and some parts where it's distinctly different. And then a word like water is just very different, and it has almost nothing in common. Who knows, this red column just might be word. It doesn't mean anything. But these, nobody came up with these variables and said column 3 means something and column 17 means something else. They're just a bunch of numbers that are being used to represent it. The colors are just showing you the range of them. And yeah. Yeah, I think the slides that I put up on Learn, actually, those was my notes were on my computer out of day two because I added some slides the other day, and then when I uploaded it, I missed adding them. So I'll update the slides after on Learn, sorry, with the extra stuff. So one of the cool things that people can do then with this is once you have a bunch of these vectors is try to figure out what one of those questions we had yesterday was, does distance and like the direction of a vector have any meaning? And with these word vectors, we can find out that they actually do. So he's trying to show the example here. The one from the paper is this one showed on the side screen. So I'll make that a bit bigger for a second. So in this one, they basically did, I don't know what the documents were, but they had descriptions, maybe Wikipedia articles of different countries. I think they did their thing on Wikipedia. And then you kind of do this like, okay, can we find any kind of common relationship between some types of words? So we know these are all countries and these are all capitals of countries, and they are related in a kind of way. And without giving that information into it and just training it on the documents, they were able to come up with this relationship. Now, this space here, we're plotting it in 2 dimensions, right? So if it's done on Wikipedia, it's probably 10,000 dimensional space. So you can't just plot it that way. So how did we plot it? What they actually did is they did PCA. So we talked about principal component analysis last week. Once you've learned these vectors for a bunch of words, right, these are just a bunch of numbers, you could run PCA on this and come up with a 2-dimensional, like find the 2 principal components in this space and plot every one of these words as a point in a 2-dimensional space, right? Because these are just numbers, and you do PCA on all of the vectors you have for like where every one of these elements of this vector is a feature, right? And what you end up getting is a space where the principal components describe the largest kind of variation in this space, right? And if you tell it 2 dimensions, it will just tell you 2. They give you the most variation. So they plot it into PCA and use PCA and plot it into 2 dimensions. And then when they just put the words down and plot their point, given those 2 dimensions, they get this relationship. And so it seems like in this direction, in the vector space, that you're talking about going from, country to capital of that country, right? And the direction is kind of, it's got a little bit of variation, but it's not, it seems like meaningful, right? And remember, this vector is actually, this is a 2D vector, but this is actually, I don't know what, we said 1,000, right? So this is actually a projection of a 1,000-dimensional vector that you could come up with, right? So you could use the PCA, the weights on the different features to work out what that direction is in the actual space. But you could just have all your data in the PCA space, and it works as well. So there's a real direction in the original space that just helps us find it and see it better in 2 PCA. So there's other examples people talked about in the paper. They talked about being able to do kind of arithmetic on them, because if you take these vectors and then add them together, you get some new vector. And so famously, one they found is they said, take the vector for king, subtract the vector for man, add the vector for woman, and it's very close to the vector for queen, right? So this kind of consistency here that, at least in this document, they only put 2 gender labels, so it's very oversimplified, but they were able to get, a pattern there that was distinct, and that pattern was embedded in the other things. So the nice thing that this shows you then is that these vectors and what you're learning here, it is actually not assuming things are independent anymore, right? That something like gender has some kind of aspect that's captured across many dimensions of this vector, and something like being a monarch of a country or being the capital of a country is represented across some other features. Things aren't assumed to be independent anymore, so that's actually really useful. so here's something that's showing a bit more example, just how they're kind of training that, right? To take a bunch of words as inputs. This for the skipgram model. Sorry, there's a blender in the background. Look at this. You have the input words and the output words, and then you're trying to come up with positive and negative examples of what should come next, right? So this idea of negative sampling can be used in many areas, but it was kind of originally used for this field. I'm trying to see, there was some other part in here that was useful to explain. It's a really, it's just a good article. The overview is a bunch of the different things, and not just from that original paper, but things that happened after. So that was why it was nice. Yeah, and so these negative words can be anywhere in the document. They could be random, or they could be other words that show up nearby, or words that you might, like, I think there's people who do it with trying to find words that are likely, like what are the next most likely ones given your model, and use those as negative examples, so that you're trying to get it to be really accurate. But really, this was just the beginning of this kind of field of doing that. So this kind of core calculation here is the one kind of to understand what they were doing, how to update that. Right, and so then the window size and the number of negative samples with these parameters I was talking about that you have to choose, because the larger the window, the more context you're going to get. And there's no right answer, right? So I had like ranges here for possible values of these. The larger the window size, the more context you're getting. If you start getting over, 10 or 20 words, you're talking about multi-sentence context. Since that may be what you want or may not, right? And negative samples, people have found that actually a very small number is still effective, but originally people were using 10 or 20 negative samples at a time. So this thing never worked. Did it? No, I had some other demo I was going to run, but it didn't work. Okay, so another way to see negative sampling is that essentially you're finding the updating the objective function that you're using for logistic regression. So sigma here is our sigmoid function that we're passing things through. And I guess ut here is the vector for all the words. And what you're trying to do is maximize this part, right, where you're saying that you're maximizing the probability of that word being right because you're using the correct sample, the correct next word, and then you're sampling j tilde or squiggly sample from a probability of some other words from the document, so randomly pick some others, and take this just their this particular approach's representation of the vector, the word vector, after you've kind of run it through that matrix, getting your probability and then adding those together, right? So but these are all negatives, right? So you're penalizing the model for picking the wrong words next and rewarding it for getting that one next. And this becomes the objective that you're trying to maximize in your logistic regression. This was also another good article just about, I'll post the link, just about negative sampling in particular, and had a bit more information just about how that process works. Okay.